Okay, so I have opened them and now I have to share my screen. Can you see it now?
Yes.
Yes.
But full screen, is there an option for full screen? Yes, perfect.
Yes, perfect.
Now it's perfectly fine.
So now it's fine?
Yes.
Perfectly okay.
Okay, good. So in your place, this is the afternoon, right?
It's
Yes.
in the afternoon. Yeah.
I see. So how are things in India with COVID and all these global crisis?
So COVID is really bad. I mean, right now we are getting 80,000, 90,000 cases. But the number of cases, the curve has flattened out little, but it's still increasing. So I mean, we feel that we are approaching the peak, but not yet at the peak. But from last 6 months, it has been a lockdown situation. I mean, for example, we in campus could not go out. In last 6 months, we did not leave the campus. And it seems that another 5-6 months is again not an option.
So, but can you, for instance, go to office or give classes or have seminars in the university? Not.
Classes are in now online mode, complete online mode.
Mm-hmm.
No students are here. We have to evacuate all the students.
Okay.
So seminars and all, everything is online mode.
Online.
Everything is online mode. Yeah. And for this semester, and also seems it will be the case for next semester also.
Mm-hmm. So until say February or so, right?
Yes, February, March, easily, it seems.
I see. I see.
Yeah. So it's really bad in India.
Yeah.
What is the situation in Spain now?
Well, the situation in Spain, they are testing many people, right? So now they are testing many people, and because they test many people, they discover that more people are infected. But the number of cases of people that have to go to hospital is quite low, right? So it's not that bad as it was in the spring. I mean, in the spring, when the first wave of COVID came, it was very bad. Sorry, there is something about my video.
Yes, your video is off somehow. Yes.
Yeah. Okay. Yeah. So yeah, in the first wave was very bad because many people were infected. Many people went to the hospital. The hospitals were full, and many people died. Right. Also, in the residencies, on the for elder people that go to residencies, right. So there were many infected people and many people died. Now the number of infected people is growing, but I think it's simply because they are testing more and they discover more cases, right? But it seems the epidemics is not, hurting so much people. But I think there is still a concern about the winter, right? Because in the winter that is now going to come soon, they expect the epidemics to be more tough, right? So we still don't know. And there are, they talk about the vaccine. Maybe the vaccine will come by the end of the year, but I think nobody has a clear idea of how long it can take, right? Because I mean, even if there is a vaccine, how long it will take until, we vaccinate millions and millions of people, right?
Right.
And a country like India, where you are over 1,000 million people, so how long it will take to vaccinate, say, half of the population or 1/4 of the population, right?
Yeah. Yeah. Professor Zuazua, I have allowed the attendees to come. So
Okay.
attendees has already started entering.
Good.
Yeah.
In university, the students are there, or it is totally closed?
Very basically, I mean, the government here in general in Spain, in Germany, in every European countries, in most European countries are being very conservative. So very little activity, say, on campuses, right? So yeah, I mean, and there is a lot of doubts about how to proceed. I mean, somehow I think some leadership is also lacking, right? So, there are different opinions, so for instance, in Spain, the ministry has decided to let regions decide. So different regions can take different measures, right? So in some universities, the final decision is to make everything online. In others is to do some kind of hybrid system in which some students come to university and some others do it from home. And actually, I think one of the problems that was discovered this summer when, because in the springtime, there were not, the campuses were closed, is that, I mean, teaching is okay. You can always teach via online. The problem was more with the exams, right? How do you evaluate the students, right? And then when you are teaching a small group, like a master course, or when you have 10, 15, 20 students, you can even have, one interview per student to make the evaluation. But when you are doing, I don't know, Calculus 1, the first academic year, and you have 200 students, you cannot do personalized exams, right? And I think we were not completely ready for this, right? So, yeah, I think among many professors, there is this feeling that, well, the teaching was okay, maybe the exams were not well resolved completely, right?
Yes. Here
I don't
also
know how
this
you
is
do the exams in India, right? So in India also you have many students. How do you do in order to do a calculus exam?
same problem is in India also, because you have in a batch you have 200 students. How you will evaluate? The process is not clear, because whatever process you choose, there are some problem there to the evaluation. It is not.
For example, this semester I'll be teaching some 600 students. I mean, I'll do a test exam.
Text.
See, for example, I'll ask them to write something small. If they can take a picture and send me back, if I can collect them back. If cannot, multiple choice questions. And if it doesn't work very well, we'll talk with the administration, maybe postpone until they come back.
Yeah, and how do you check that they have done this really in a confidential manner, that they are not using other sources or?
Yeah, this we cannot guarantee anything. I mean,
Right.
we have to do our best. Jumble the question, jumble the orders, make 10, 15 question sets. So, and each question will appear one after another. They cannot see the whole question paper together. So steps like this been taken from, but we have to go on actually.
Yeah.
Okay. So, Professor Zuazua, should we start?
Yes, please go ahead.
Yeah. Okay. Okay. So, on behalf of the organizers, a very warm welcome to Professor Enrique Zuazua and all the participants of webinar on PD and related areas. For the participants, we request you to keep your questions stored in the question and answer box. Now I kindly request Shishendu Chaudhary to take the session forward.
Thank you, Prashanjit. So we are honored to have Professor Enrique Zuazua with us today. Professor Zuazua holds a doctoral degree in mathematics from the University of the Basque country, Spain in 1987, and the Université Pierre Curie, France in 1988. He is currently affiliated with 3 different academic institutions, namely Friedrich Alexander University in Germany, University Deusto Bilbao in Spain, and Université Autónoma de Madrid in Spain. His field of expertise covers various aspects of applied mathematics, including partial differential equations, numerical analysis, control theory, optimal design, data science, and industrial transfer. He is currently serving as the Director of Chair of Computational Mathematics at University of Deusto. He has been awarded the Euskadi Prize for Science and Technology in 2006 and Spanish National Julio Rey Pastor Prize in 2007. He was an invited speaker at International Congress of Mathematicians ICM 2006 in the section on control and optimization. Lot of study material is provided in his webpage. I suggest students and young researchers to have a look at it. Today, he will speak on Turnpike control and deep learning. Professor Zuazua, it is over to you now.
Thank you, Sisendu. Thank you, Prosenjit and Sisendu and all colleagues that organize this seminar. For me, it's a great honor, and I am actually very pleased to see you all, even if it is through Zoom. We have met often, both in India and here also in Europe. I remember you, Sisendu, as a young student in Toulouse, in Bangalore, and I'm glad to see that yeah, you are with your colleagues doing so successfully. And certainly this webinar initiative is a great thing so that we can all gather again. So yeah, Turnpike control and deep learning. This is a topic in which we have been working for now a number of years. Actually, my interest on this, in some sense, started by questions that were formulated to me by a former PhD student, Francisco Palacios, who now works in Boeing, California. That was back in 2005 or so. He was a PhD student in our team in Autónoma de Madrid, but simultaneously he was working in Airbus, Spain. And the topic of his lecture, of his PhD, was optimal shape design in aeronautics. And for me, you know, of course, aeronautics is about fluid mechanics, and for us, fluid mechanics is like Navier-Stokes equations, and Navier-Stokes equations are time-evolving problems. They are beautiful Cauchy problems. Actually, we know that one of the $1 million problems is still open, you know, for the 3D Navier-Stokes equations. And I observed that, however, most often in applications, they were considering optimal shape design problems on a steady state configuration, without time. Of course, we also understand that if you drop time from the PDE and you go from, say, the time evolution problem into the steady state one, then you are reducing the complexity of the problem. Of course, shapes are now only depending on space. There is no time. Everything looks like simpler. But somehow I was curious about what is the justification from the perspective of the optimal shape design theory of why you can remove time in a problem in which, in principle, you know, time evolution is so important. So I have bring here a reference, a very nice, say, survey article by Alonso and Colono. You know, Juanjo Alonso, he works in Stanford, in university in the US, in the group of Anthony Jameson. I mean, they were, Anthony Jameson is one of the, say, pioneers on the systematic application of the techniques of optimal control in the aeronautics community. And in this article, they consider the problem of the sonic boom minimization for the new generation of supersonic aircrafts. And of course, the challenge is to design, you know, new, aircrafts so that the sonic boom that supersonic, traveling generates when getting to Earth is minimized, so to fit, to be in agreement with the increasingly demanding restrictions for civil aviation, right? And this is a control problem in long time, simply for the reason that, you know, the sonic boom takes a long time to get from, you know, the height in which this is generated until Earth, right? So this is a case where you see there is a time evolution problem, there is a shape to be optimized, and time is long, right? So the key message of this lecture is that actually in many problems, you know, the same could be said about climate change. We are talking about, you know, the years to come, you know, the centuries to come, the future of Earth, right? So we are thinking on a long time horizon. We are talking about economic growth, right? We are thinking in terms of years or even longer, right? Decades and so on, economic growth of a country. We are talking about chronic diseases, you know, people that have some problems like chronic, like diabetes or high pressure, so they normally are medicated for the rest of their lives. So there are many problems in which, you know, there is certainly a dynamical system to be controlled, but actually one of the most representative features of that problem is the time horizon is long, right? And most often, when you look to the existing math literature on control problems, you will see that some people do it in the steady state regime, like elliptic equation, right? Or the steady, say, Navier-Stokes equation. Some others do it in the context of time evolving problems, but very rarely people look at how the length of the time horizon will affect the control strategy. And this is what we are doing, right? Then the application to machine learning is quite natural. There has been a lot of investigation in the recent years about machine learning neural networks. They can be reformulated in some cases as time discrete dynamical systems that if you think in a more abstract fashion, you can even think on them as being the time discrete version of, say, the dynamical system continuous in time. And therefore, these ideas of, say, long time control, Turnpike control can be also implemented in that setting. And this will be the second part of the lecture and the justification of the title, right? Turnpike control and deep learning. When we wrote the first article in this topic back in 2013 with Alessio Porretta, we were precisely trying to do this. We were trying to explain that, you know, at least in some model examples like linear finite dimensional system and linear partial differential equations, this is a Science Journal of Control article back in 2013. We did also with the heat equation and the wave equation. We were trying to explain why and how and when the long time horizon control problems can be approximated by steady state ones. So we sent this paper for publication. You know, the referees were very positive, and one of them said, well, maybe the author should look to the theory of Turnpike. So at that time, I never heard that word. I looked Turnpike on Google, and then I find that Turnpike refers to a highway in the US. And actually, there is still indeed a theory coined by John Voigt Neumann, the Turnpike theory, because he already observed that oftentimes in the context of game theory in economics, for many problems, you know, in long time, right, the strategies which are optimal are nearly a steady state. And this is why when you look to the, for instance, the interest rate that the Bank of Europe, America, and probably in India as well, they fix for the interest rate of loans for, say, 6 months. They normally do it for long time horizons, like 6 months. They say 0.25 during the next 6 months. They could do it variable in, you know, in time. They could do it today is going to be 0.25001, and tomorrow is going to be 0.24999, and the day after will be again 0.249899. But then, you know, they say, well, we know according to the Turnpike theory that in long time horizon, say in 6 months, the result of doing this very complicated, say, strategy, control strategy, will be most essentially the same as just, you know, taking a steady 0.25, okay? So this idea was further developed by Paul Samuelson, who has a book on this topic. He actually got the Nobel Prize in economics later. So in some sense, it was a rediscovery in the context of partial differential equations of something that was already in, you know, well known, at least in some particular instances of time discrete dynamical systems in finite dimensions. Actually, there is a book by Zaslavsky back in 2006 on the topic. There are also articles by our colleagues, for instance, Lars Grune here in Germany in Automatica 2013, where they deal with time discrete systems arising in economics and looking precisely to this question of Turnpike. So now, just to make a graphical representation for those that are more interested on ODEs or PDEs. So what the Turnpike theory says is that optimal trajectories and control strategies look like, say, path indicated in this slide, right? So the time horizon is long, so the control and the trajectory have the possibility to fluctuate, but actually what you observe is that in the long time horizon, most of the time, this optimal trajectory is in a steady state, right? So you see how this optimal path that is represented there, and that, you know, with a shortcut, you could make a quasi-optimal strategy in blue. What the theory tells you is that if the time horizon is very long, what you should do is first compute the optimal configuration for the steady state problem, forget about time, And once you know this, say, intermediate, stationary optimal configuration, from the initial datum, you go there, you stay there as long as you want, and then in the end, you exit. And actually, I represent this in this drawing in green about the midpoint in an airport. This is actually what you do when you are meeting friends you make in an international airport. So how do you do this appointment? You say it's very easy. We will meet in the meeting point, right? And for doing that, what you do when you land, you walk, you go to the meeting point, you sit there, and you simply wait until the others come, right? If you think a little bit on this, you will realize that most often in your life, in our lives, we are implementing this kind of Turnpike idea without really, having, thought of their or its, mathematical motivation. This is also what you do when you take the train. I mean, you rush to take the train, and once you are on the train, you simply sit or you stand and you wait until the train arrives. And when the train arrives, you take off. You do the same on the elevator. And as I said, you can discover this paradigm of quasi-constant control in many, many applications, in particular, for chronic diseases where, the doctor tells you, okay, you should drink this infusion every day or take 2 pills, one in the morning and one in the afternoon also for the next, say, month or so, okay? Now, what was a bit struggling for me was, okay, if this is true, that the Turnpike principle is so universal, why don't we see it in PDEs? So why, I mean, for instance, I take the wave equation, you compute optimal controls for the wave equation and you see oscillatory patterns. But nobody's surprised because you see, people tell you, well, I mean, that's natural, right? The wave equation, you take the Fourier representation or you do the characteristic propagation analysis, and people tell you, well, the wave equation is signals are oscillating. This was already said by Fourier. They are ping-pong, back and forth. And therefore, it is natural also that if you have to control waves, right, the control will have to produce anti-waves to compensate this oscillation, and the control will also oscillate, back and forth, right? So here, this, principle that waves oscillate and the controls of waves have to oscillate as well does not depend on the length of the time interval, right? Maybe the amplitude of the oscillations will change, but the fact that this is a purely oscillatory endless pattern will not change. So why don't we see Turnpike for wave equations? Okay, maybe it's because the wave equation, there is no dissipation built in the system. Let's look to the heat equation. This was already computations that were done in the late 80s by Glowinski and Lyons, right? You read their articles in Acta Numerica on the numerical approximation of control problems for PDEs, and they have this kind of drawings. They control the heat equation, and they see that surprisingly, even though the heat equation is slowing down and going to zero, the control seems to do the contrary. The control is very smooth, nice, and moderate in the beginning, and then in the end has a huge amplitude, and it starts, oscillating like crazy. Again, you don't see any Turnpike phenomena there. You don't see that the control is flat during most of the time interval. And again, in this drawing, I have taken the time interval to be 0, 1, but if I will make it longer, I will see exactly the same picture. Actually, when you zoom in the end of this, say, time interval, you can see this kind of fractal oscillations, right, that increase endless, like in the typical Tikhonov instabilities for the heat equation. So what is the explanation? Let me give you the explanation in the context of the heat equation, where things are very clear. But you can do the same for the wave equation, for Navier-Stokes equation, and so on, right? So you take the heat equation in a domain omega, Dirichlet boundary condition, diffusion of heat on a domain omega, in a cavity omega, and I am controlling, I am heating through, an applied force or heat source F in the small cavity, small omega, as drawn there, down there in green, right? So the control is localized, but because of the Gaussian diffusion, we expect this control to diffuse into the whole time space interval along time in the whole space domain. And therefore, in a time window, capital T, we expect that we will be able to regulate temperature to bring it to the desired temperature. In this case, the target I denoted as Y star, okay? This is the classical control problem. how do I handle this from an optimal control perspective? Of course, I could deal with more sophisticated issues like controllability or null controllability, but I will not get into this today, not necessary at that point. So if you simply proceed by optimal control strategy, you will say, well, the goal is then to minimize a cost functional that has two pieces, one in which I penalize the cost of the control, so the norm of f, the control in L2 squared, and the other one that penalizes the distance to the target. In some sense, if I minimize this functional, maybe I will not get exactly to the target, but I will get to it, close enough with a control with a, say, moderate size. Of course, I can also use penalization and multiply any of these two terms in the functional by a constant parameter going to infinity, so to enhance the fact that maybe I want to be close to the target, or by the contrary, I want to not to use too much control. Now, when you apply here the optimality system or the maximum principle of Pontryagin, what you observe is that what the theory says is the line in blue down there is the control F is given by the solution of the adjoint system phi. And when you look to the adjoint system, in this particular case, you see that the adjoint system solves the adjoint heat equation backwards in time. And then you understand why the picture that Glowinski and Lyons were discovering, right? Because when you draw how the solutions of this adjoint equation evolve, of course, they evolve like those of the heat equation, but in the reverse signs, in the reverse sense of time. So that in the final time, they are huge. And when you go backwards in time towards zero, then they slow down and they stop oscillations, as it occurs in the heat equation, where in the last time asymptotics, say the last time asymptotics of the solutions of the heat equation look more and more exponentially like the first eigenfunction of the Laplacian in the domain omega. So you see that nothing is wrong. Actually, you solve this optimal control problem and you recover this pattern that Glowinski and Lyons already found numerically. They were right. And there is no Turnpike. So why not Turnpike in this case? Is because we are dealing with PDEs? What's going on? So in fact, you see that in both examples, the heat and the wave equation, we see that there is not apparently Turnpike. In the case of the heat equation, because the control is given by the solution of the joint problem that is developing this pattern, according to which the maximum energy and oscillations arise in the final time. And the case of the wave equation, where the solutions are purely oscillatory of sinusoidal type. Again, because the control is given by the adjoint equation. Excuse me. So now, how can I try to understand this better? So let me go back to the functional I was minimizing. So far, I was minimizing the two terms in black, f squared and the distance to the target. But why, if we integrate or incorporate to the cost functional also the size of the state, right? So I add an extra term in the functional that I am minimizing. Is just the norm of the state in L2 y squared, integrated in space and time. This is actually very natural, right? Because you don't only want to, not to consume too much control. You want, of course, to get close to the target, but it's also very natural to avoid, too high oscillations on the solution of the trajectory you are trying to control, okay? Now, when you do this, of course, this new problem has also a unique optimal control. This functional is quadratic, convex, actually strictly convex, continuous in the space L2 small omega cross 0t for the control F. So there is a unique minimizer. You characterize this minimizer by the Euler-Lagrange equations. You get this optimality system. And the difference you see now is that because I have added this, say, red term in the optimal cost to be optimized, the cost to be optimized, I see now that in the adjoint equation, there is a coupling between the state and the adjoint state. So now you cannot say immediately how phi behaves, right? Because in order to say how phi behaves, you need y, but you see that in order to compute y, you also need phi. So this is a fully coupled system. And actually, when you compute the spectrum of those systems, this type of systems, which is now fully coupled, one is the forward heat equation and the other one the backward heat equation, you will see that actually the spectrum, as drawn down there, splits into the left part and the right part of the complex plane, indicating that the complete dynamics of the system is constituted by a manifold that is stable in the forward sense, and the other one that is unstable or stable in the backward sense. And this is precisely what explains that when you now redo the computation of the control for the heat equation, but penalizing also the state, not only the control and the target, but also the state, now you recover this Turnpike principle. So then the message is then the following. In order to have control, right, Turnpike property in control, right, is not only depending on the PDE or the model under consideration, it actually depends, right, on the functional, the cost functional you are minimizing. When the cost functional is coercive enough, both in the state and the control, you will recover the Turnpike. But if for some reason you, as originally in the previous, say, examples I gave you, you ignore the size of the state and you simply penalize the size of the control, then you will not get this kind of Turnpike principle, but rather you will reproduce the complexity of the original dynamics of the system, right? Okay, so now in order actually to prove this, now if you want to really prove without ambiguity that the spectrum of this, say, optimality system is really away from the imaginary axis, right? In order to show that there is this exponential, say, convergence to the steady state, to then, you know, later in the final time quit also through some small, say, boundary exponential layer at the final time. If you want to do this, you will also need controllability properties, right? And this is somehow already implicit in the example I gave you in the beginning, when I said, well, what is Turnpike principle? I mean, you go to the meeting point and you wait there. You see that in order to get to the meeting point, you need your system to be controllable, right? If the system was not controllable, it could well be that even if there is an ideal steady state configuration, you cannot get there, right? So you really need first to control the system to get into this steady state, to then be allowed to remain in there, time independent, and to later quit again, you know, along a controllability, you know, arc in order to get to the final target. So the second message is be careful. If you really want to see the Turnpike property, you will need to be dealing with problems in which you have a strong controllability properties. But this is the case, for instance, for the heat equation we are considering here with control in a subdomain, or for the wave equation under the classical, say, characteristic geometric control conditions. Okay, that's it. Now, of course, if you are doing numerics, you have to be careful about numerics as well, because you are computing controls in long time, right? So if you want to recover, right, the correct dynamics of the controls in long time horizons, you will need to use numerical algorithms that are well behaved in the long time, right? And this is, for instance, the example, the classical example, when you look to the symplectic integration of Hamiltonian systems, right? In which you want to employ numerical algorithms that are able, for instance, to capture the periodicity of the solutions of an harmonic oscillator. So you see in this example, we know that we are solving an harmonic oscillator. This is the phase plane, say, analysis. We know that the actual solution of the ODE is this periodic, say, circle in red. But if you apply classical Euler explicit or Euler explicit, you will never discover this periodicity. If you will apply the Euler explicit as drawn, you know, up on the left, you will see a trajectory that turns around but goes to infinity. While if you do Euler implicit on the top right, you will see a trajectory that is shrinking and converging to zero. So you know that if you really want to keep the periodicity of the original continuous dynamics in the discrete setting, you will need to use an appropriate, say, Runge-Kutta algorithm or method which is so-called the symplectic one, right? The same happens in PDEs. Oftentimes, you are probably familiar with this terminology when you look to hyperbolic systems, that you are looking for algorithms that are well-balanced meaning the same, right? It meaning that the numerical algorithm is able to capture the long-time asymptotics of the continuous dynamics. Now, as I told you, we began by analyzing this in the paper with Alessio Porretta. Let me tell you briefly what we did, just to understand. So here is formulated in the finite dimensional context, but the same applies in a semi-group context as presented in that article. What we did was the following. Okay, let's consider the simplest linear finite dimensional dynamical system. A is the dynamics of the system, B is the control operator. And then we minimize a cost functional in which I say, well, I want the trajectory to be close to a given target, X star, during the whole time interval. You see, in order to recover the control, I penalize, the Turnpike, I penalize both the control and the state, right? And the state, maybe I don't penalize the full state, I just penalize some projections through the matrix C. So I have three matrices, A for the dynamics, B for the control, and C for how much I am penalizing the state into, the cost functional. When I write the optimality system, drawn, down there in blue, I know the control again is given by minus B star P, where P is the solution of the adjoint system. But of course, the adjoint system and the state equation for X and for P are coupled together through the right-hand side terms, which depends on the matrices B and C. And now the question is, do I see the Turnpike, right? How do I define the Turnpike? Well, it's very simple. You say, what was the Turnpike principle? The Turnpike principle was ignore time and look to the steady state optimal control problem. So how do you do that? Very simple. A dynamical equation, you consider steady state equation, AX equal BU. This could be an elliptic PDE or simply as in this case, an algebraic system. And then rather than considering the functional you are minimizing, which is an integral in time of U squared plus CXS minus X star squared, you just take drop of time and you consider the same functional in the steady state fashion. Again, this functional has a minimizer that you can write down according to this optimality system, right? Now you see you have an optimality system depending on time, P depending on time, and you have an optimality system, U bar, P bar, which is independent of time. What is the Turnpike principle? The Turnpike principle says that if, both for the state and the adjoint equation, you have the right, say, controllability, observability, or stabilizability properties that in this finite dimensional case can be simply represented by the Kalman rank condition, right? What the theory says, under these two conditions, right, which in some sense require that the control operator is strong enough to control the dynamics, and on the other hand, the penalization term C in the cost functional on the state is also strong enough to guarantee that you are penalizing the full state, then you have this exponential Turnpike property. And you see, this exponential Turnpike tells you that both the state and the control simultaneously, depending on time, are exponentially close to the steady state X bar and U bar, right? But you see that on the right-hand side, you have two exponentials. Normally, when you look to Lyapunov stability or the lifetime asymptotics, you are interested on how, the time goes to infinity. But you see, in this case, the time belongs from 0 to capital T, and capital T is going to infinity. So there are two boundary layers in the beginning and in the end, as represented in this blue line. And this is why you have on the right-hand side term in the bound, you have two exponential terms. One, taking account of this initial boundary layer you need in order to get into the steady state, and the final boundary layer you need in order to exit, okay? This is the theorem. And now what is the proof? We have basically three proofs, right? You can have a look to our papers, and I just give you a hint. The kind of three proofs we have is, the first one is to say, well, I would like to prove this using Lyapunov-like ideas, dissipativity. What is the dissipativity principle here? Well, it's actually that when you look to the product of a state and adjoint state, basically xp. If you take the scalar product of xp, x minus x bar, p minus s bar, p bar, and you take the scalar product in the Hilbert space where the dynamics is evolving, you see that the time derivative of this is behaving like a Lyapunov functional, because on the right-hand side, you get a negative term in which you see both b star applied to p and c applied to x, right? So the proof is a bit more tricky than the classical Lyapunov setting. Why? Because in this time, the time doesn't go to infinity, but simply goes from 0 to capital T. Then you have to somehow, out of this dissipativity law, you have to work integration by parts and energy estimates in order to guarantee that the boundary layers at t equals 0 and t equal capital T are not an impediment to get this exponential convergence result. The second proof is Riccati theory. What is Riccati theory? Riccati theory is to say, well, you know, it's known. If I take the linear quadratic regulator problem in infinite time, so essentially I consider the same kind of minimization problem, but in infinite time, you know, the Riccati theory tells you that the optimal control is given in a feedback manner and that the trajectory converges exponentially to the steady state. So what are we doing when we are looking to Turnpike? We say, well, I'm not in infinite time. I'm working in a finite time, 0 capital T, right? And because I'm working in 0 capital T, there is a terminal condition, yes. So, but then in the end, this kind of, say, linear quadratic regulator problem in which you see the exponential convergence towards 0 is the first step in the iteration in order to build the optimal trajectory in time capital 0 capital T. What do you do? If time 0 capital T is very long, you simply take this exponentially decaying curve, you chop it off, and then the only thing you have to do is, by an iterative algorithm, make small increments and corrections on the final terminal condition so that you match the terminal condition of the adjoint state. Okay? This is the second step, or the second proof. And the third proof is a proof more inspired on the theory of singular perturbations, as we like to do in PDE often, right? When you are working, for instance, with optimal shape design, you say, well, I have my control problem, xt plus ax equal bu, on the time interval 0 capital T, but for me it's hard to handle the fact that I have the same model in time intervals that are changing, right? So I prefer to bring the problem into a fixed time interval. How do I do that? By a change of variable in which I go from the variable t belonging to 0 capital T into the variable s varying from 0 to 1. So I make the change of variable small t equal to s time capital T. And now s in the new equation becomes a, say, pseudo time variable. But when you do this change of variable, you see now that in the new time variable with respect to s, you have a parameter 1 over t, capital T, penalty parameter. So you see that when t goes to infinity, capital T goes to infinity, this 1 over t goes to 0, right? And you see how somehow in the asymptotic limit, the steady state optimal control problem emerges. Okay, this will be the third type of proof. Now, what happens with nonlinear problems? That is very interesting. You know, so far I only spoke about linear problems, and everything was explained in terms of the optimality system and controllability properties and the fact that the cost functional is coercive enough. But what happens when you go to nonlinear? Think on a fluid model like Navier-Stokes or some variants of that, right? Let me just to explain you the great difficulty that we encounter in this topic at the nonlinear level is, let me explain you this very simple example. So you take the cubic heat equation. So it could not be better, right? So the cubic heat equation is the PDE, which is nonlinear, but is maybe the most nicely behaved. Solutions are global. You have a nice energy that is decaying. Solutions converge, you know, to 0 when in the absence of control. There is an exponential decay. So everything is perfect. So if you ask me to solve this optimization problem, right, try to find the control F that is minimizing both the size of the control and the distance of the solution to a given target, reference solution YD, right? This could be, for instance, the ideal temperature in our room. I choose, for instance, YD to be 19 degrees. Okay, then I choose YD to be 19, and I try to keep the temperature in the room to be, as close as possible to 19, according to the, to the heat source I can really afford to pay, right? This is why I penalize also the control on the cost, right?
Professor
There is a
Zuazua,
unique, yeah.
We have some questions in the chat box. So can we take that questions now?
Yeah. Let me see if I can find.
So
How
one
do
is,
you know the
yes.
adjoint problem is solvable directly? I mean, this is a very good idea, actually. So if
But this is
the adjoint systems are very tricky. So the adjoint systems, I mean, the optimality systems, which are written here, down there, right? The optimality system, which is written there, is a system coupling the state equation and the adjoint equation. So if I will ask you, can you solve this problem using PDE techniques? It will be very difficult to do it because one equation is forward in time, the other one is backward in time. So actually, we know that this, say, system is controllable, or sorry, we know that this system is solvable, right? Because this is simply the Euler-Lagrange equation associated to the minimization problem under consideration. And the fact that the functional has a minimizer is very simple. It's just the fact that the functional, you apply the direct method of the calculus of variation. The functional is convex, coercive, in a Hilbert space, continuous, then you have a minimizer. And because you have a minimizer, in this minimizer, the Gateau derivative is equal to 0. And when you write down the Gateau derivative, you have the optimality system. So normally, in general, and this is the case systematically when you apply, control techniques and Pontryagin maximum principle, these systems look tricky, but they are solved, they are solvable because there are critical points. This is when you do, like when you do for your students Lagrange multipliers. You say, I minimize the function fx under the constraint gx equal c. And then you say the Lagrange multiplier technique says that in the minimizer, I know that the gradient of f is parallel to the gradient of g. Now I ask you, how do you know that there is a point in which the gradient of f is parallel to the gradient of g? Well, if you know that the original calculus of variation problem has a solution. Because if there is a solution, by Lagrange multiplier, you have, this optimality system. But you are totally right in this question. It's not an exercise you will be able to solve applying, in principle, semigroup theory or Galerkin approximation for solving evolution problems, right?
Another question is,
yeah, what is the interpretation of adding the L2 norm both in space and time of the state in the minimizing functional? Well, actually, this is something we do all the time, right? So, when you are deciding, you take Google Maps, you want to go from one place to another. Actually, I have taken in one of the slides, there was the Google map for going from where to where. It was, let me see, it was from, Mumbai to Calcutta, right? Right. So normally, when you try to say design an optimal strategy, normally you try to avoid oscillations that are too large, right? Yeah. So you will say, well, maybe there is a better way. You have to go very far, and you say, well, not. So let me just take my standard path. So normally, when we implement a control strategy, we have the tendency to avoid oscillations that are too, say, wild, also on a state. How to show the well-posedness of the coupled system for the linear case is the same, as I explained before. It's not the solvability of these coupled systems is not something you understand by applying, say, classical PDE or semigroup techniques. It's actually a corollary of the fact that there is a minimizer for your problem. I insist that these optimality systems or the Pontryagin maximum principle is a generalization of the Lagrange multiplier rule, right? And you know that the Lagrange equation gradient f equal lambda gradient g has, say, a solution, right? Because right, you are able to solve the, say, the minimization problem, right? It's the same as why for the Laplacian you have a first eigenfunction. How do you solve the eigenfunction problem for the Laplacian? Well, you can do it by minimizing the Rayleigh quotient, right? Okay, good. Thank you for your questions. So maybe I can continue now?
Yes.
Okay, thank you. Okay, so now back to nonlinear. Everything is perfect here. Well, you know, you still discover some new features in this problem. Now, the PD is very nice. The functional looks very nice, but be careful, the functional is not convex anymore. It cannot, I mean, it can be that it's not convex, right? The convexity is not guaranteed. Why? Because even if the function looks quadratic, the dependence of the solution I on F is nonlinear. And therefore you are taking a square of a nonlinear function, the convexity of that functional is not guaranteed. Despite of this, the functional is coercive, there is enough regularity on the solutions of the heat equation, there is enough compactness, so you can prove the existence of the minimizer, right? And because you have the existence of the minimizer, again, for the same reason as before, you have a solution of the optimality system. And the control is given by this optimality system. Now you see things get more tricky because you see the state equation is given by this cubic heat equation for y, and the adjoint heat equation is the adjoint of the linearized system. This is why you get this term 3y squared phi. And now I ask you, can you prove the Turnpike property for the solutions of this adjoint system? Well, now this adjoint system or this optimality system is nonlinear. How are you going to prove the Turnpike property if the problem is nonlinear? Well, one possibility is to say, let's do as we do classically in the theory of PDEs. I linearize the system. I prove that the linearized system has the Turnpike theory, the property, and then by, you know, nonlinear perturbation, I try to go back to the original system. Okay, but when I say I linearize this system, I linearize around which state? Well, because we are looking here for the Turnpike property, it will be very natural to linearize around the steady state problem. So the algorithm is, you first solve the elliptic optimal control problem. That's very easy. You take a solution, you call it y bar, say phi bar for the elliptic optimal state and optimal adjoint. You linearize the system on that point. And what you see is the first two equations in the top, right? You see the linearized equation of y is given by z. And of course, because I am linearizing y cubed, I get a term which is 3y bar squared, y bar being the steady optimal configuration, times z, and then the control on the right-hand side. But you see, when you linearize the adjoint equation, you get something trickier, right? Because you see in the adjoint equation, minus phi t minus Laplacian phi, there is a nonlinear term which is cubic now, but mixing phi and y is 3y squared phi. Therefore, when you linearize this, you have to linearize both with respect to y and with respect to phi. And this is why, when you linearize that equation, what you see is that the structure is the one I am formulating there. You see the term in red is very nice because it's the adjoint of the original equation in the top for z. But then, due to the linearization of this, say, cubic term 3y squared phi, you also get an extra term on the right-hand side, which is multiplying the state z. And this is actually, in this case, just the second derivative of the cubic function. You get 1 minus 6y bar phi bar. What was the proof we did with Porretta? We said, well, if I have to prove that for this linearized system, I have the Turnpike principle, I would like to associate this to the optimality system of a linear quadratic problem. What is the linear quadratic problem? Well, it's very simple. I take the heat equation satisfied by Z, where now there is a potential 3y bar squared, but this is a potential P of x, very nice heat equation, positive potential. there is a control F. This system is controllable, no problem. And the optimality system corresponds to the minimization of this functional in which I minimize both the cost of S and the cost of F and the state Z. But you see, because of the blue term in the top, I have a multiplier rho X in the penalization of F squared. And what is this multiplier rho X? Is 1 minus 6 Y bar phi bar. Oh, that's strange. Because this multiplier rho, in principle, is not necessarily non-negative, right? It could change sign. But on the other hand, the only way in which I can say that this nice quadratic optimal control problem has a solution is when rho is positive, right? In which case the functional is really quadratic, definite positive, and I have a minimizer. So you see, in order to guarantee that this linearized theory applies, so to go back to the nonlinear and deduce that I have a Turnpike property for the nonlinear, I need rho to be positive. But how do you prove that rho is positive? Rho is 1 minus 6 times something. And this product of a state and adjoint state, in principle, doesn't have a sign. So Y bar, phi bar, our condition is we impose Y bar and phi bar to be small so that the product of Y bar, phi bar is small, and therefore rho is positive. And in this sense, I have the Turnpike property. But what do I need in order to guarantee that the optimal steady state Y bar and phi bar, the adjoint state, are small? Well, what I need is to assume from the very beginning that the target YD is small. So the conclusion is, in the context of the nonlinear parabolic problems, or in general, nonlinear PDE, we can extend the original theory developed in the linear context for PDEs of Turnpike. We can extend it to the nonlinear context, but under the assumptions that the targets are small, right? So the conclusion of this first part is, doing the theory of Turnpike is challenging. We understand it more or less well in the linear case. Doing it in the nonlinear case is still widely open, except in the case where the targets are small, right? Otherwise, it's very tricky. We don't have a good understanding of the Turnpike property. But despite of this, what I wanted to convey with you is the fact that even if we don't have a proof of the Turnpike property for the nonlinear problems, this is always something you can use, right? In which sense? What is the message you have to keep? The message is, the analysis is difficult, but the principle is easy. And in particular, it's easy to understand and to implement. How do you implement it? Well, you take your dynamical system, drop off time, produce the steady state problem, optimal control, optimal design problem, solve the steady state problem, and then simply use the controllability of the system to enter the steady state, remain there, and then exit again, right? And this is what is drawn in these trajectories, which are not, they are not solutions of the optimality system because they will be smooth otherwise. This is simply drawn in this schematic, say, quasi-Turnpike principle that I invite you to keep in mind as a remedy to solving complex optimal control problems in long time intervals in the dynamical setting in which computationally and dynamically it will be quite complex. Okay, so this is the PDE part. In principle, motivated by classical problems like aeronautics, climate change, economics, medical therapies, and so on. Now we are in the age of data sciences and machine learning. People are looking to data, right? They want to classify data. I mean, this is a particular example in which you want to classify, waste, right? Plastic, paper, glass, other, you are classifying images in Google. You want to distinguish, one person for another, right? There are many, many possible applications. You want to identify the author of text based on, the way the text is written, or you want to identify faces or voices, right? You want to identify patterns everywhere. So this is actually mathematically in the context of, say, data science and machine learning, this is often, you know, interpreted as a huge, say, interpolation problem, right? You have objects, xi, right? Many of them. It could be images on internet, millions of them. And you would like to classify them, right? So allocate them to each of these images, xi, a label, yi, which is the name of the person it corresponds to, right? So actually, this is why you go to Google Images, you put the name of a person, and you can get many images of that person in different circumstances, right? Of course, sometimes this is not completely correct, and you see that some images are mixed, right? So this allocation of labels Y to, say, objects X is not necessarily perfect. What does it mean? It means that rather than trying to make an, say, completely, you know, 100% correct and accurate classification, which will require certainly a nonlinear process that is, you know, of a complexity that is unaffordable, right? Much beyond the cost of dimensionality. You try to make a simplifying, say, ansatz so that you get an approximation which is accurate enough with some small error, but still very useful in order to classify the objects you are willing to deal with. Okay? So how do people do that? Well, they do it using neural networks, right? This is all explained in our recent paper that you can find in Archive with in collaboration with Carlos Esteve, Borjan Geskowski, and Dario Piguin in our team. You can find it in Archive. The title is Large Time Asymptotics in Deep Learning. You identify these two ideas, right? Learning, say machine learning, but also large time asymptotics. And all this is based on the classical paper by Sivenko, right? Sivenko, it was back in '89 or so, who said, listen, we know many density theorems, right? We know by Stone by Strass that polynomials are dense in the space of continuous functions. You go to Sobolev spaces, LP theory, Lebesgue spaces, Sobolev spaces, you know that say infinity and compactly supported functions are dense also, generally, right? Of course, you have to avoid examples like L infinity and so on. But in general, you have, you know, very robust density results. What Sivenko said, listen, you can also prove density by employing functions that rather than being polynomials, they are sigmoids shown in these shapes, right? Say two typical sigmoids are this kind of arctangent function, which is a smooth transition between 0 and 1. And the other one is the so-called ReLU, which is simply a rectified linear function, means simply that is the positive part of X, right? These are two typical sigmoids. What Sivenko said was, listen, you can get also the density by simply, you know, combining, making compositions of such sigmoid functions, sigma. Now, when you think on what a composition means, you immediately get into this neural network kind of discrete dynamical system. What is this discrete dynamical system? Drawn, you know, written there in the top. It's simply you say, okay, I have a state, right? These are the objects I am trying to classify, right? And classifying objects is like, you know, putting reds to the left and blues to the right, as drawn in this figure down there, right? So just separating red and blue. And in order to do that, using the idea of Sivenko, who says that every map in the Euclidean space can be approximated by composition of these sigmoids, what this actually means is that I am generating a time discrete dynamical system in which out of the initial configuration where red and blue were maybe very mixed, right? I built a nonlinear mapping in which I do simply two things. First, out of the vector X, I simply apply a linear or affine function, right? So I translate with B and I multiply by W. So you have to see that B and W are playing the role of the controls. And once you apply this control B and this control W, you apply the nonlinear function sigma. And in this way, you have a dynamical system, which is discrete in time, which is nonlinear because the sigmoid sigma is involved, right? But which is, after all, a control problem. And what do I want to do? Well, I want to, as I do in optimal control in the first part of the lecture, I want to minimize certain functional. Which is the functional I would like to minimize? Since I want to separate, I would like, for instance, reds to be to the left, blues to be to the right. This is I analyze loss functionally in the final, right? And then I also, of course, as usual, I penalize the controls because I cannot afford controls B and W that are too large, right? So now you see that this is a time discrete problem. The number of iterations I do in time, this is what is called the number of layers on this deep learning time iteration, time discrete iteration. But you see that once you formulate the problem that way, you know, deep learning and time discrete control are, you know, twins. So there was a variant of this. People said, well, you see, these time discrete optimal control problems are very nonlinear because of the involvement of the functional sigma. It is better to, you know, it's easier to understand if we think on in small increments, right? So rather than, you know, jumping with sigma from one state to another, what was proposed in residual neural networks, this is why they are denoted by res nets. What was proposed was to say, well, why don't we make small increments, right? So then rather than going directly from x into xk into xk plus 1 through the mapping sigma, let's simply use sigma as an increment state xk. And then in that case, you have a small parameter h, which is making the increment of the state. Now, once you see this, you say, oh, but now this time discrete incremental or residual time discrete dynamical system looks very much like a discretization of this ODE down there. And now I am led to the ODE, in the square there, where you see, oh, now this is something I know, right? Because this is x prime t equals sigma wt, which is a control applied to the state x plus b. And now I am penalizing both the control and the final target. The final target being the classification problem in which I want red to the left and blue to the right. Okay, so it looks very, very, very similar to the problem that I started originally, where I wanted to simply regulate temperature so that at the final time, the temperature was the one I wanted. Okay, so this looks very familiar. Now, once you have this, you can say, well, maybe the notation is a little bit different because the nonlinearity here is sigma, and the control here is called W and B. But if I formulate it in the classical context, what I have is simply an optimal control problem for a nonlinear ODE. Now, UT, the control, will be the pair WB, and the state will be given by X, and F, the nonlinearity, is simply given by sigma, equal F. Now, what does it mean to have many layers, many iterations in my machine learning algorithm, in this neural network that is trying to approximate a very complex, say, nonlinear function? What does it mean to have many layers? Well, it means n is large. So that n large is t going to infinity. So we are talking about control problems in long time horizon, right? So here, just to avoid the difficulties related to the compactness of the trajectories in nonlinear problems, here what we have done is, this is just an analytical comment. Rather than penalizing the controls in L2, I just penalize them in H1. In that way, I have the needed compactness in order to guarantee that there is a minimizer. I have a minimizer. I write the optimality system. I try to pass to the limit. And then what happens when t goes to infinity? Well, when t goes to infinity, I expect some kind of asymptotic simplification, right? And this is what we do in our paper. Actually, in this part of the paper, we use the penalization strategy in which you see that, a time horizon that is going to infinity is better to think on a pseudo time s going to from 0 to 1, and then seeing 1 over capital T as a penalization of the time derivative of the state equation. And then this brings you down to, to asymptotically to, the optimal steady state configuration. And this is what is written in that theorem using, say, kind of Lyapunov techniques for the proof, right? Let me show you how this works, right? So look at the left top. This is the decline of problem, right? You have a population of blues and a population of reds. But the blues are surrounded by the reds. And you say, well, I'm not happy with this. I need reds to the left and blues to the right. So now you have to build a dynamical system that out of this initial configuration here, blue surrounded by red, they evolve on the plane so that eventually reds are to the left and blues are to the right. So I show you what the video does, right? And you see 3 different instances of the same problem. The only thing that changes from one to another is how long is the time interval, right? So in the top, the time interval was not long enough, so the distribution of right and left, the separation is not so good. In the blue, in which the time interval was intermediate, the distribution, the separation is a bit better. And in the last one, where the time interval is even longer, you see that the separation, the splitting is nearly ideal. There are still a few reds in the blue area to the right, but it's nearly perfect. So you see in this example how when time increases, you improve, right, the separation that the neural network guarantees. Despite of this, you see, when you look these trajectories, they are quite complex, right? They are, turning left and right. You see the dynamical system is like very oscillatory, very, very twisted, right? This doesn't look like the Turnpike property. This looks more like the original examples in which I was showing. You can control a dynamical system, but in order to do it, the trajectories have to oscillate very much. Why is that? Remember, in order to have actually, the Turnpike property, what I said is that when you look to the optimal control problem, not only you need to penalize the control and the final target, but also the state along the time interval. And this is what we do in the second part of the paper. Now we say, in the second part of the paper, we also penalize as down there, not only the control, but also the state along the time horizon through this tracking term, now within the integral from 0 to capital T. And then, in that case, again, defining as Turnpike, say, a steady configuration, the optimal steady state, we are able to prove this exponential convergence theorem like we do in the context of, say, the Turnpike for optimal control problems. So you see now that, again, in the context of, say, residual neural networks, in the context of deep learning, you see again the two phenomena. Optimal control, in which you are successful in long time, but to the price of trajectories that are oscillating along. But that when the time horizon is long, but the functional to be minimized takes into account also the tracking term, behaves much more nicely in a Turnpike manner, being exponentially close to the Turnpike, right? And this is what you see in this simulation, right? In which, I don't know whether I took the video. Yeah. So this is the video in which now the classification is even much more, say, successful. And you see, as drawn there, a better, say, behavior of the trajectories with less oscillation. So let me just conclude. I wanted just to you keep in mind two open problems in case you want to work on this. One is you can formulate it in the PD setting, in the ODE setting, or in the deep neural network setting. Doesn't really matter. As I told you, when we are dealing with nonlinear problems, normally the Turnpike property, we can prove it analytically, and then smallness conditions on the targets. So doing it for large targets is something that is widely open. This is the first problem. And the second problem is that when you look to how people implement this kind of machine learning algorithms for, say, through neural networks, you really see that actually, with respect to the formulation I have done here, they adopt a more complicated formulation because they allow themselves not only to evolve in a discrete time setting, as written in our, say, formalism, right? But actually, they allow themselves in every time step of this discrete time dynamical system to change the dimension of the Euclidean space where the state is. So you can start from 2D, go to 3D, then go to 6D, go down to 5D to end up in 2D. And this fact that, you know, the dynamical system is switching in the Euclidean dimension of the state is something that you cannot cope with a classical, say, ODE representation, because by definition, when you are dealing with ODEs, you say from the very beginning how many components are on the system, and you immediately define what is the dimension of the Euclidean space in which you work. So actually, the most really complete interpretation of these machine learning algorithms will be more in the context of switching ordinary differential equations, in which there is a lot to be understood also from the Turnpike perspective. And with this, I'm sorry it was maybe a bit long. I finished my presentation. I thank you very much for your attention and invitation, and I am at your disposal for any question you might have. Thank you.
Thank you very much, Professor Enrique Zuazua, for such a lucid talk. So we have received some questions from the participant. I'm just conveying to you, and I also have a question. So
yeah, I think the first one was the Kalman rank condition was before, but I forgot to answer to that question. I mean, the Kalman rank condition simply says, I think it's here. No, it should be maybe here, right? No, here, right? So, I mean, this goes back to the 50s, right? When people said, okay, take this in infinite dimensions where everything is much easier to be understood, right? So this is a linear control system. In the absence of control, U is the control. Take U equals 0. Then the dynamics is simply given by x prime plus ax equals 0. So the solution is given simply by exponential minus at. This is the semigroup. And this is the free semigroup. Now, depending on whether the eigenvalues of A are real negative, real positive, or imaginary, you will have oscillatory patterns like for waves and Schrodinger equations, or you will have some kind of, say, nice exponential stability as you do for the heat equation. Okay, but this is the free dynamics. And now you say, well, but now I am allowed to control the free dynamics by adding a perturbation U, a control U to the system. Now, this perturbation, this control U, enters into the system through the operator B, right? Why? Because this is like the hidden problem, right? As I said before, right? As I said before, let me go back. In this heating problem, typically, you want to heat a building, but the heater is not occupying the whole building. Otherwise, you will not, you could not get in, right? The heating is localized, by the walls or in some rooms, and you expect that despite this localized heating effect, this heat will propagate everywhere. So normally, when you control a system, you don't control in each of the components of the system. You just do it in some of them, right? And this is actually what you are doing here. And then the question is, what are the conditions between the matrices A and B that need to be fulfilled so that just acting on the system through the matrix B, you can guarantee that you control all the components of the system? And it turns out that the sharp condition is this Kalman rank condition here written in 6 in red, which says that the only thing you have to guarantee is that the rank of B, AB, A square B up to AN minus 1B is equal to N. When the rank of this great matrix is full, the system is controllable. If for some reason the rank was less than N, was N minus 2, it means that there are 2 components of the system that you cannot control, right? And actually, for those that are interested, this rank condition is the same as the one that later Hormander found for the hypoellipticity of partial differential equations. There was another question in the chat was, is there any result to handle general nonlinearity or some characterization theorem? Is the minima for a stable equation is not unique, which minima to take? These are very interesting questions. So thank you for these very interesting questions. So when you go to the nonlinear case, right? Where was nonlinear? Was somewhere here, right? So this was nonlinear. Okay, yeah, there are papers, I didn't show you here a list of references that we have written in this topic. You will find in particular some papers by Sebastián Zamorano, a former postdoc from Chile. He's back in Chile now, Sebastián. And he has written an article on the Navier-Stokes equation. So if the target is small, the same I have said here about the semi-linear heat equation, you will be able to do it for Navier-Stokes, right? Provided the target is small, right? When the target is large, we don't know how to prove the Turnpike property. And actually, as indicated in this question in the chat, it turns out that when the target is large, there could even be more than one steady optimal state. So when the optimal steady state is not unique, there is more than one, which one do you take in order to build your, say, Turnpike strategy? You go through the gate red or through the gate blue? Well, in this case, it's clear. I go through the gate blue because blue is deeper than J, and then the cost will be smaller. But when they are both identical, this is not so clear. So this is why, in the case of nonlinear dynamical systems in which the target is large, the Turnpike theory needs a substantial completion and further work. Because first, the steady state problem might have several minimizers. And therefore, if you want to prove the Turnpike, you should really first be able to show that for every optimal trajectory, the optimal trajectory goes through one of these steady states. And of course, if you want to gain a better comprehension, you should also be able to say which is the gate that every trajectory, chooses. Okay, so this is still widely open, right? But in particular, there is a paper by our former PhD student Dario Piguin, in which he proves that in semi-linear elliptic optimal control problems, when the target is large, there can be more than one global minimizer, what makes the Turnpike property to be challenging in that setting, right? Sir, could you share the slides PPT of the session with us? Yes, of course. I can try to send you by Google Drive. Okay, so Shirshendu or Prosenjit, I will put this online in my Google Drive and then I will send you an email, right? Because this might be a bit heavy because of the videos to share online. Sorry, by email. Okay, but I will definitely do this with pleasure.
So
and then you can show these, right?
So I request all the participants, if they have some questions, so they can raise their hands so that we can pass it on to the speaker. I think someone has.
Hello.
So he has.
Hello, you can ask the question.
Hello, sir. Good afternoon, sir. Good evening, sir. Good afternoon. I have one question, sir. Can I ask to that sir?
Well,
Yes.
you can also ask as you go by voice or in the chat.
First
We
of all,
can hear you.
thank you for giving wonderful talk, sir. I have one question, general question. So if you see day by day temperature is increasing, so that means the energy is rapidly increasing, so that abrupt change in the environment. So you have talked about this control problem. So how do you control this energy with respect to time? Is there any mathematical model is existing, sir?
So are you referring to this drawing here? Are you referring to this drawing in which you see that the temperature is increasing, or? So you see, I mean, I mean, the question is very interesting. So here I have taken the heat equation, right?
Yes, sir.
But I could have taken an unstable heat equation, say yt minus Laplacian y minus, say, 10 times y.
Okay.
Then in that case, this heat equation will be unstable.
Okay.
I mean, if 10 is larger than the first eigenvalue, there will be some components of the system that will be exponentially increasing and the other ones exponentially decreasing. But everything remains the same. Even if you have this destabilizing potential or you add some convective term, you know this system is controllable. And therefore, our theory applies, and you will end up finding this, say, Turnpike property. I mean, this is a very good question. So the Turnpike property has nothing to do with the stability of the system. Why? Because you have control. And the control allows you to first stabilize the system towards the steady state and then remain there. Right? So, but this is why you are totally right. In order to guarantee that a system has the Turnpike property, you need some stability properties, right? And then your question is, what happens if the system is unstable? Well, you see, the control is there for that. You stabilize first, and then once you have the system under control, you can keep it within the steady state and to let it free again in the end, just to match the terminal condition. But somehow, in this theory, what you see is that the control allows you, or should be there, through sufficient controllability conditions to stabilize the system in case there was some unstable branch.
Thank you, sir. Thank you.
De nada. Ciao. Thank you. Thanks to you. Very nice question.
Anybody has any other questions? Okay, then I have two questions here.
Yeah.
So one is that one, since you are considering essentially when due to the Turnpike property, the control corresponding to the steady states, right? So
Yeah.
is it reasonable to consider the optimal control problem in the beginning itself a control which doesn't depend on time?
Sorry, the control doesn't depend on time here, right? Because I'm considering optimal steady states.
No, but I am asking about when you consider the evolution problem, in that time, if I consider a control which doesn't depend on time.
Oh, right. Yeah, that's a bit easier, right? So actually, this is we did it in the context of, say, the problem with Porretta. Actually, when you read, I mean, here I was not completing my references. Let me see if it is there. Yeah, I mean, this is the second paper with Porretta. You see, the first one, 2013, we wrote the linear case. And then in the second one, 2016, this is a proceeding article. It's on my web. Otherwise, you let me know and I will send it to you. We do the nonlinear case. And when we started working with the nonlinear case, we immediately realized this was tricky. And actually, the presentation that we have done here about linearizing and then understanding this business of the raw multiplier and then assuming that the target is small in order to make this multiplier to be positive and so on, was our second attempt. In the first one, in that paper, we explained that things are much easier when you take the control F to be independent of time. Because then it's more like a gamma convergence theorem, right? Then even if the PDE under consideration is time evolving, the control only depends on X. So the control belongs to L2 of omega, right? Is parameterized with respect to capital T, right? But then you are dealing with a much simpler question in which you say, well, is the control F, which only depends on X, depending on the parameter capital T, does this control converge to the steady state optimal control? And in that case, we prove that this is basically a gamma convergence argument using the Lyapunov stability of the system. This is much easier, right? But our result is like the one I have mentioned here in the context of deep learning, right? I was a bit fast here. What we say is that this convergence occurs along subsequences, right? Why? Because in particular, it could be that there are several minimizers for the steady state optimal control problem, right? So although the answer is in principle simpler when F depends only on X, there is still room for a better understanding of this problem, in particular in the case where the steady state optimal control has several minimizers, right? Because then I will ask you, well, if the time dependent, in the time dependent problem, the control converges to some steady optimal control, to which one it does it, right? Or can the control oscillate between several of them, depending on the length of the time interval? This is still an interesting topic indeed. And actually, in that proof we do with Porreta, even if we try, we don't succeed on proving convergence rates, because due to the exponential stability of that system, you could even expect that not only the optimal control f of x, depending on capital T as a parameter, converges to the steady state optimal control, but you could also expect that this convergence is exponential with respect to capital T.
Okay. And just another question, small question in that you have, because for this kind of Turnpike property, essentially you need something you told about again stability or controllability, so that you can come to the close to the exactly to the steady states. But suppose you don't have controllability, some kind of approximate controllability, you know. So can we do something? We can stay close to that Turnpike, that steady states.
This is a very interesting question, Shishendu. Thank you for asking that one. It's somehow a bit discussed in this paper, in the first paper with Porreta, right? But there is not a complete answer to the problem. So when you look to that paper, you will see that we consider, for instance, the wave equation in the absence of the geometric control condition. This is a typical example in which you have approximate controllability, but not exact controllability, right? And then we prove some kind of, say, Turnpike in average. Turnpike in average simply meaning that we are not able to prove these point-wise, say, stability properties, right? Like in here, we don't prove this point-wise exponential proximity, but just the proximity of the time integrals of these quantities, right? So we have some kind of, in time average, you have some kind of weak Turnpike, but the quantification of this Turnpike is not done in that paper. And actually it's an open problem. And as you know, when you miss the geometric control condition and you have only approximate controllability, when you do feedback, you normally don't get the exponential convergence rate in time. So it could well be that if you quantify these Turnpike properties in the absence of the exact controllability, one should expect also a weak Turnpike where this exponential decay here has to be replaced by some polynomial weakly, Turnpike or even logarithmic, right? This is a very interesting open problem. Thank you.
So thank you so much for making this session successful. We hope to get your participation in future talks.
Of course.
Prashanjit, over to you now.
Thank you, Shirchandu. Yeah, thank you, Prasanjit. So it was for me a great pleasure. I'm very glad to see that you are all healthy on that side, and hope that the pandemic is over soon and we can again meet here in Europe or maybe in India, right? I have very good memories always of my trips to your country. Thank you again. All the best.
Thank you. Thank you very much.
Ciao. 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 Bye.
Yeah. So
yeah,
I request everybody to leave the platform now.
Okay.
And maybe we'll see. I mean, we'll see in 2 days for the talk of Professor Yehuda Penchover.
Okay.
Thank you, everyone.
Maybe Pinchover. Okay.
Yeah.
We will try to join. Thank you. Bye.
Yeah.
Ciao.
Yeah. Thank you. Thank you, all the participants. Please leave the platform now. Thank you all.